No, you won't. Until you try, you'll never got it.
All right, welcome to WASA Distance Education. This is MBF3C, grade 11 college prep math. And I'm Pete, I'm your teacher. And today we're back in the studio, so things are back to our routine. So who do we have from Winneman on this morning?
Ernie.
Oh, hi, Ernie. All right, glad you're able to log on there. Great. So, okay, so we will be just kind of picking up where we were yesterday. We were looking at all the trig identities, and I am going to go on to the next lesson, but I want to go back a little bit because I'm not sure how much you got from yesterday's lesson. It was a little bit awkward. I was talking on the phone. As a matter of fact, I'd be curious to if you were listening in, send me a note, send me a Facebook message or whatever. Let me know how it was. Were you able to hear me well? Were you able to follow along? Because we were up in North Caribou Lake yesterday broadcasting, a little bit of a dodgy setup. I'm trying to figure out better ways to do that, and we'll certainly do it better next time somehow. All right, so I'm just going to do a quick little review of the trigonometry, and then we'll move on. One of the things that I didn't really get to was the problem solving, and whoops. Okay, let's try this again. I seem to be okay. All right, I don't know what button I just pressed. Hopefully it's not too bad. Okay. So now. Okay, so I'm not going to go through the whole thing, but I'm just going to sort of remind you a little bit about the different ratios that we have. So the point of the trigonometry ratios, SOHCAHTOA, the point of those is to help us work out specifically right triangles. Okay, now that's a triangle that has a right angle in it, and it has a right angle by the little box. Doesn't matter what the triangle looks like, because a lot of times it won't be all that straight, right? It might look like that or something. But if someone puts out a little box there, well, okay, that's exaggerated. But if someone puts out a little box there, they're guaranteeing you that angle is 90 degrees. Okay. So we have three different ratios, and it's the sine ratio, the SOH in SOHCAHTOA. The SOHCAHTOA comes from this up here, right at the top of page, I guess it must be page 3, page 2. It's just a memory aid, a mnemonic for remembering the ratios. And now that you've seen them all, it might make a bit more sense. It's sine is equal to opposite over hypotenuse, cos is equal to adjacent over hypotenuse, and tan is equal to opposite over adjacent, SOHCAHTOA, right? Now, you can, how are you going to memorize that? I like to think of it as meaning I love triangles, SOHCAHTOA, I love triangles. Maybe that'll help you. Maybe you could come up with a better way to memorize that, okay? So we have the three different ratios, a sine, a cos, and a tan, okay? And they all depend on what angle we're looking at. So the first thing when we get a right triangle, we identify that it's a right triangle by that little box at the right angle. Make sure that when you draw a right triangle when you're doing trigonometry problems, you always draw that little box, because that's important. Because otherwise, if you don't draw a little box, you're not guaranteeing me that it's a right triangle, which means that you can't really use the trig identities, the three trig ratios. Okay, so draw the little box, and then everything will be set. So the first thing you do, you draw your box, or you find the box if you're doing a problem, and then you look as if you were sitting on that box, okay, looking out, and you're going to see the H, the hypotenuse. So I always recommend that you draw that in. Okay, every new piece of information you get when you're solving trigonometry or any geometry problem, draw it on your diagram. Of course, you're going to have a diagram. whether they tell you to make a diagram or not, it's an excellent idea to organize your information on a diagram. So yeah, draw the H. Now all you have to worry about is whichever angle you're working on, which sides are which, because the hypotenuse is always the same, but the offset and adjacent always depend on which angle you're dealing with. Okay, the adjacent is always the side that touches the angle that you're working on, and the opposite is the one that doesn't. If that's easy for you to remember. So we have the sine ratio, and again, the sine by itself is just a ratio. It's just a number, but we can use it with the inverse sine function to take that ratio and turn it into an angle in degrees. Okay, so that's how we use it, and we can use it in a couple of different ways. I'm just kind of scrolling through this. We can find a missing side right here, for example, the hypotenuse. So we can use that sine ratio to find a missing side. And then the other thing we can do with it is use it to find the angle itself, right? And the way you do that is you come up with, you find the ratio. There's the ratio right there. And then you take the inverse sine of both sides. This is about the bottom of page 5. Okay, so what they could have done here is put one more line in there. You know, we don't do this typically, but you could say inverse sine sine A, you know, equals, and then something. So right in there. But then what this reduces to is just angle A, right? That's all it is. So we don't do that. We just go from a sine A equals this, and then you basically take the inverse sine of both sides and you turn sine A into angle A, and you turn the ratio into a value in degrees. And they always use the approximately equal sign. So if you draw a regular equal sign, it's two parallel lines. If you draw an approximately equal sign, they're two wavy lines. And if you want to see what one of them looks like, it's usually on your keyboard, right up beside the 1 key, right to the left of the 1 key. There's one of them right there. So if you type that on your keyboard, you'll see it. It looks much better than mine. And so really all you're doing is you're making two of those parallel to each other. Okay. And that means, what that literally means when I read that as a math statement, that in my head it says approximately equal. Okay, that's exactly what I read. So I would read that in my head, say angle A is approximately equal to 52 degrees. Okay. Okay, so that's the two things that we can do with the sine ratio. We can find an unknown side, either the pretty much any of the sides. We can also find the an unknown angle. Okay. So what the cos ratio does for us, the cosine ratio, it does the same thing, but it allows us to find that information if we have a hypotenuse, which we need for the sine, and an adjacent side. Okay. Now, and that's fine, right? So it really depends on what we have, which one of those two ratios we're going to use. If we have a hypotenuse, then chances are we're going to use either sine or cos, depending on whether we have an adjacent or an opposite for the angle that we have a number for, or if we have an adjacent or an opposite and then we need that angle, then we're still good, right? Now the other thing that we can do, and I'll just kind of skip through this, is we have the tangent ratio, and that's the last of the three of them. And the tangent ratio is good when we don't have the hypotenuse, right? We don't need the hypotenuse. When we need adjacent, opposite, or the angle, and we have two of those, right? So we don't even need the hypotenuse, okay? And we can work through it. Now, of course, we could always use the Pythagorean theorem to find the hypotenuse if we have the adjacent and the opposite. So, and that's really what these trig ratios give you, is they give you a way to get enough information about the triangle that then you can start using your other tools, right? we know how to find a hypotenuse using the Pythagorean theorem. And so if you, for example, had an opposite and you had an angle, but you didn't have the adjacent, you could work out the adjacent using the tangent ratio. Then you have an opposite and adjacent, which is this leg and that leg, and then you can very easily find the hypotenuse. Might have to kind of refresh your memory of the Pythagorean theorem there, but you can do it. So, and then they gave us some problems to do, and now this part of it isn't decorated. I haven't added a lot of stuff to it because I didn't have a pen yesterday. So let me go back to this diagram for a second, because a student, and if he wants to take credit for it, he can. All right? You want to take credit for pointing this out? Okay. All right. Well,
That's okay.
okay, so Ernie pointed this out to me. Okay? And it's just a mistake actually in the book here. So it's page 12. We're talking about the tangent ratio. Okay? The tangent ratio. And from SOHCAHTOA, T-O-A, tan, right, equals opposite over adjacent. That's the ratio. But the diagram, it looks like they copied the diagram from something else from the coast. So really this line here doesn't go here, it goes there. That's really where it goes. This is not correct on this diagram. Okay, so it's just a little glitch. There are actually a few glitches in this lesson with some of the examples not showing all of the steps or missing some notation. So, read through it with just kind of a one eye, kind of a wary eye. And I actually advise you to read any examples with a wary eye. Okay, no matter what you're doing in math, anytime you see an example and you're reading through it, I suggest doing it alongside and doing it yourself, because you'd be amazed at how many mistakes there are in math books. You'll also be amazed at how many math teachers make mistakes. It's terrible. It's awful. Okay. So, and if you see that, if it's a book, you really can't do much about it, but you correct the book. I would suggest you just write in the book and correct it, so that somebody else doesn't run into that. If it's a math teacher, you can probably just raise your hand and say, type a little chat message and say, hey, I don't think so. Okay. It's worth it, whether you're right or wrong. It's usually amusing to get called out on a mistake, and it teaches us stuff. We don't learn from doing problems that we know how to do. We learn from problems that we have trouble with, that we don't know how to do. Okay, that's why when I'm telling you about the support questions, I'm telling you, do the support questions. If you do a couple of them, if you get them right, then move on. Right? That's why, because you learn from the ones that you struggle with. So we found the tangent ratio, and they have a fairly complicated way of showing you how to manipulate the equations that you're going to get, right? But for example, for this one, tan 43 degrees equals 15, and we're going to give those units. It really kind of bothers me that they're not showing units in the book, and I'm going to get that one fixed for sure, because trigonometry is all about measuring stuff, so we can't just have unitless numbers unless they're the actual ratios. So anyway, so this is what they show us in the book, and now they spend the next couple of lines here trying to get this x, which I'm going to change to blue, trying to get this x by itself. So let me show you how I do it. Okay, I'm going to show you how I do it. When the x is in the bottom and some known is up here, watch this. We're going to say x equals okay, so what did I do right there? I just swapped them around, right? That's logically what happens, right? That is what I do. I just swap them around, and look at that. So they they kind of went through a whole bunch of stuff there, a whole bunch of lines to try and convince you that to just swap them around. But there is a method to their madness in the book, so I'm not discounting it. It is correct. But here's what they're doing logically. I'm just going to or what they're actually doing. What they're actually doing to get rid of, if you have tan 43 degrees equals 15 meters over x, and you want to get x by itself, you're going to have to multiply both sides by x. Okay? So then once you multiplied both sides by x, you can cancel, whoops, let me back that up. That was nice. You can cancel the x on that side because x divided by x is 1, no matter what x is, right? So now if we rewrite this, we have x times tan 43 degrees equals 15 meters. And so now what we're going to do is we want to get rid of that tan 43 degrees to put x by itself. So all right, let's try it. So we're going to divide both sides by tan 43. Tan 43 degrees. Okay, so we divided both sides by tan 43, but on the left-hand side, they cancel each other out. Why? Because tan 43 is some number. We don't care what it is. You can work it out on your calculator if you want to, but tan 43 in the numerator and tan 43 in the denominator are the same number. A number divided by itself is always 1, so it does not matter what tan 43 is. We're allowed to do this. So let's rewrite this. So x equals 15 meters divided by tan 43 degrees. Okay, so what I ended up with after going through all these steps is what I ended up with here, which is that I just swapped these two around. Okay, as long as you understand why you're doing it, there's no problem going from this step right here to this step right here. Okay. So try it a few times with the practice questions, the support questions. Make sure you can do that step. Show the extra steps if you have to, if you feel it's necessary for your understanding of it. But I'm not going to say anything if you're going from that first step to that second step, because that's exactly how I do it. Okay, but in my head, I'm doing all these other steps that I put in the little green squiggle on the side. Okay, and I'm basically, the textbook shows you pretty much the same thing. I think they take a few extra steps even to do that. Okay. All right, so the whole point then is that when you get one of these ratios, you're going to have a little algebra problem to solve to isolate the variable, the unknown, which could be x, it could be n, it could be something, right? We just name it whatever's convenient for us. When the text gives us a question, they'll name it x, but it could just as easily be called AB, because that's the name of that side as far as our naming conventions, right? It could also be called, it'll be called, it could be called little c as well, because one of the things, if an angle is labeled with a capital letter, then the side opposite that angle is usually labeled with the small letter. So that would be little b, that would be little a. So those are some naming conventions that you might get. Okay. And really the point of the naming convention, there's not a right or wrong answer. There's the naming convention and all the variables we use, it's to get us to the right answer. So you got to sort of pick naming conventions that are that work for you. Okay, so now they gave us some support questions, and we kind of looked at this yesterday anyway. I know we don't have any information on here, but we definitely looked at these yesterday. But the one thing that we didn't look at yesterday, and what I really want to get to, is answering these word questions. They have some pretty interesting word questions here. There it is. In the key questions. So the key questions are pretty much up until the word questions are right out of the examples. So if you see a question like calculate this right here, you can go look in the examples, or you can just kind of figure that out what they want. The problem is that they don't show any examples in the text on how to do this sort of thing. Question 8. A guy wire. What is a guy wire? All right, this is a support wire. Okay, no, it really is called a guy wire. I'm not making fun of it. It's just it's a word that outside of some professions they probably don't really hear. What it is, when they hold up a big antenna, if you ever drive by a big freestanding antenna, like one of these really tall ones that's made out of tubing, and and usually has lights on the top. If you look carefully, you'll actually see that there's a bunch of very thin metal cables coming from the top, spread out around it, usually 3 or 4 or 5 or 10 cables, and those are called guy wires. Okay. So yeah, and you might not even see them if you're just driving by, flying over. So it supports a vertical power pole. So that's how it keeps from falling over. They basically build it on a little platform, and then they use wires to keep it up rather than having to dig down really, really far. They just use wires to hold it up. Anyway, so it's the guy wire. It's that thin wire that we're looking at here. So the thin wire, it supports a vertical power pole. So, one of the assumptions we can make then, and I'm going to erase that little annotation I made. So one of the assumptions that we can make then is that is a right triangle. So when you come to that conclusion, when you make that assumption, go ahead and draw your right angle in there, because that's gonna help you. And then just label that H for hypotenuse. Okay, you'll probably make a much better H than me. Okay. So this is the first step really of the 4-step problem solving model. We're trying to understand the problem. We're trying to gather the information that we need, okay? And then we can make a plan of attack. So the wire is fastened to the ground 9.5 meters from the base of an 8.7 meter tall pole. So it's 8.7 meters tall. That's what that 8.7 meters is right here. But what it doesn't tell us is that it's 9.5 meters from the base. It's 9.5 meters right there. They didn't tell us that. That's the base. There's the wire where it's attached to the ground. So now I'm educating my diagram. Okay, I'm adding stuff to it that I haven't even calculated yet. I'm just adding stuff to it. Calculate the measure of the guy wire and the ground. The measure of the guy wire and the ground. So I think what they want is that angle right there. Okay. Now, one of the things that I sometimes do if I add information to it, new information, I'll change colors, maybe use a different style or something. All the stuff I put on it so far, I think, is stuff that came right out of the question. Okay. All right, so what are we going to do here? Well, we have, if you wanted to rewrite this, because it's a diagram, you could rewrite it. There's no real problem there. This is 8 point, sorry, I think it's 8.7. Let's see. Oh, whoa, okay, well, that's it. It's 8.7 meters is the length of this side, 8.7 meters. The length of that side is 13.5 meters. And the length of that side is 9.5 meters. Well, that pretty much tells us everything we want. And we want angle A or angle X or angle whatever. You can name it whatever, right? You can name it, maybe you can name it Pete or something like that. Okay, I use letters. It's a little easier to write. So that's what we're trying to find. So what can we use, right? What ratio will we use? Well, let's see. We have the hypotenuse. We have, for as far as angle A goes, we have the opposite. We have the adjacent. So we have every single trig ratio that we could possibly want. And the hard part about this question is to figure out which one to use, because we can use them all. This is a rare case that we can use them all. So let's just use the sine. Okay, so the sine of A is equal to the opposite, which is 8.7 meters, over the adjacent, over the hypotenuse, 13.5 meters. Okay. So there we go, right? So we're gonna get some number out of here, right? And then we'll say that sine A equals some number. Okay, you can calculate that. And then the next line, angle A equals the inverse sine of whatever number that was. Okay, and then because it's a word problem, you're going to say, what it asked? The measure of the guy wire and the ground. So the angle, right, you could say measure, of the guy wire and the ground. Anyway, the guy wire and the ground is whatever, and then you're gonna say what that is. Okay, so that's how you do this problem. Now, don't forget that this number here. Oh yeah, so sorry, there'll be one more line here. So angle A equals, and then some number in degrees. Okay, so sorry about that. It'll be one more because you'll have to show that, and then you actually give the answer there. So that's how you solve this sort of problem. Now you see my writing's kind of big, and I drew an extra diagram which I may not have needed, and I'm really struggling to squeeze that into the space they give. So seriously consider doing these on a separate sheet, the word problems.
Excuse me.
What's that?
I used different.
What, yours is different?
Yeah, well, it was probably the same angle, though.
Yeah, it should. The question, if the side lengths are different, then it'll probably be different angle. But as long as everything's written out, it'll be fine. I'll be able to figure it out.
Okay.
Yeah, it may be that you have an older copy of it. So if that's the case, check with the DEC there and see if you can see if you have an older copy.
I think it's the same one.
Yeah?
A different formula. So.
Oh yeah, if you use COS, yeah, absolutely. COS will work, TAN will work. That's the thing about this one. This question is one of those rare ones where any of the three trig identities will work. As long as you pick the right sides, the correct sides to use. Yeah. Oh yeah, exactly.
Right.
That'd be kind of interesting to see which one everyone picks. This is the hard part about this is that you're given too much information. All right. So, okay. So now, and then the next one. Whoa. All right. I gotta go click this thing over here. I don't know what just happened. Whoa. All right. Sorry about that. It's just I must have leaned against the smartboard or something. I don't know what happened there. So now here's a bunch of other types of questions. And here's again, a ladder leaning against a wall. There is absolutely no room in here to put that question because you will need a diagram. Okay? Please don't try this question without a diagram. So what we'll do then is I'm just going to make a space at the bottom of the page, and I'll show you how to do that. Because all these ladder leaning questions, I mean, it seems maybe here. I'm going to just add another page right here. So this is question 5. This is KQ. I don't know what we're on. KQ11. Question 5. So we have a ladder, 5-meter long ladder leaning 3.7 meters up a wall. Okay, now remember when a ladder, this is our wall, okay, and all right, this is our wall, and then this will be the ground, and then our ladder, I'm changing, okay, this is going to be our ladder right here, okay, this is our ladder, okay. And it's kind of interesting, as they say it's supposed to be 4 feet out for every 1 foot up, or 1 foot up for every. There's some rule that you have to follow, and that actually turns out to be you're basically using a ratio, right? So the ladder then leaning against the wall. The ladder itself is 5.0 meters long. 5.0 meters long. Wow, did I ever? 5.0 meters. That's the length of the ladder. And I just have my problems here. Okay. Oh, well. So that's the length of the ladder. Just ignore the fact that I goofed on that. And then the wall, it says that the wall, it's up 3.7 meters from the wall. So this is, I'm showing you this because it's not real clear in the text how to solve these. They don't really show you. So when they say it's up 3.7 meters up the wall, that's what they mean. It doesn't mean the wall's 3.7 meters. It just means that the ladder touches the wall 3.7 meters above the bottom of the wall. And you can always assume that it's on the ground. And then of course you're going to assume that any proper wall is going to be at a 90-degree angle to the ground. So I wrote that 90-degree angle. What else? what is the angle the ladder makes with the ground? Aha, now they're making things tricky with. Let's call this angle A. Doesn't matter, we'll call it X. So there's angle A. Now all we have is what? Right here. As far as angle A is concerned, this is going to be the opposite, right? And that one's going to be the hypotenuse. So it's up to you now to solve this problem. You've got your diagram. Make sure you draw that diagram. And it's up to you to pick the right trig ratio to solve this problem. And that's why I wanted to show you this. The diagram is really important here. And as a matter of fact, it's so important that if you draw me a diagram and let's say you botch one of the numbers, but everything else is correct, I'm going to give you most of the marks for that question because, it's really just it's the equivalent of a arithmetic mistake. And you've seen it if you've handed work into me. I don't take huge marks off for little arithmetic mistakes where it's, maybe you've misread your calculator or you were texting with your thumbs on the calculator buttons instead of pushing them with your finger. That happens and it's not a huge deal in math, right? Because we check stuff. But it's the problem-solving process that you get the marks for. A diagram for something like this, I can't imagine trying to do it without one. So put one in there, please. All right, so there's your ladder question. How about question, did I say 5? Wow, I meant 9. I meant to say 9, I think. Maybe there was a question 5 I was supposed to do too. Anyway, that's it. So question 10, now, was there a question?
I accidentally touched the button.
Oh, okay. Oh, that's fine. Yeah, I'll see. Okay, I'm glad I'm not the only one that accidentally presses the buttons here. So question 10, it's about a kite. Now, I know that, some of us have flown kites. Maybe some of us haven't. So basically, somehow this person has a kite string that's anchored to the ground. Okay, so this is the kite. It's flying up in the air. Okay, that's the kite. And so the diagram shows a little kid holding it, but it's actually angled to the ground. Okay, and the string is 100 meters long. So that's what we're talking about right there. So part of the trick of these questions is to figure out what, translate those words into a diagram. And then once you have your diagram, then you can educate that diagram and then figure out which ratio you're going to use. So that's step 1 is the diagram really in this type of thing from the problem solving model. And then step 2 is figuring out what you have and then what you need. That's step 2. That's your plan of attack, or if you want to be less violent, that's your strategy for solving the problem. Okay, I think of it as more like crushing the problem. You're going to attack the problem and just beat it up. Maybe that's not a good way of thinking about it. So the kite has a string 100 meters long, anchored to the ground. Oh, the string makes an angle with the ground of 68 degrees. Oh, this is going to be good. 68 degrees right there. Remember, include units in everything you do because trigonometry is all about measuring stuff. So everything has to have units. Okay, except the ratios themselves, which are unitless. Let's see. What is the horizontal distance of the kite from the anchor? So this is not, there's no actual line going down there, but what they're actually saying, and this is a pretty common problem actually in out in the world, is they want to know what this distance is right here. What is the distance, the horizontal distance? That's the horizontal distance, right? But with your knowledge, you could probably answer the other question, which is what's the vertical distance. You have enough knowledge now to do that. But anyway, all they want in the question is the horizontal distance. Now I used X. I could have used H for horizontal. Well, then that could be confused with height. I could have used H. I could have used D for distance. I could have used anything. I just used X because it didn't take me too long to think about it. Okay, so now you know, and now hopefully you can pick up your trig ratios. If this is angle A, you're off to the races there. Okay, so make sure you include that diagram. It's a key component of working out the triangles. Now, question 11 is another ladder question, so hopefully you'll be able to handle that one, draw a diagram and everything. And then question 12 is another word problem, or it's a opinion problem. So give that one a try. It doesn't give a point value this time, but it's probably going to be a few points. So the acronym SOHCAHTOA is often used in trigonometry. What do you think each letter stands for? Give an example finding either an unknown side or an unknown angle using a portion of this acronym. So in other words, TOA. Use TOA and draw a little diagram of something where TOA would come into play. Okay, so that should be pretty straightforward. But give that one a try. I know it's not numbers, but it's sort of you're using your words to communicate about math. And that's an important thing because, when you start using this, people are going to expect you to explain what you came up with, and that's why we want you to use some words here as well every once in a while. Okay, well that's it for the trigonometry lesson. I probably took a little longer on that one, just because it's important, and I want to make sure you have a good foundation for where we're going with this. So what I'm going to do now is I'm going to introduce the next lesson, which builds on the trigonometry. I won't get very far into it. We only have maybe about 15 minutes left. But I'll introduce it, and it'll give you time to think about it. And then tomorrow we'll come back and we'll have another go at it. All right, so let's take a look at this. So the next one is, it's called the sine law. So sine law. There you go. Okay. And so what we've been doing up till now is we've been using right triangles. The trig identities only apply to triangles that have a right angle in there. Okay. So what we want to do now is expand our horizons to any triangles, and that's where the sine law. We'll also be learning about some of the other laws that we have. We're going to expand our horizons and be able to work with any triangle. It doesn't have to be a right triangle. Okay. So that's where we're going with the sine law. And basically it leads to think of each one of these as a tool in your toolkit of geometry skills, of math skills. You're going to be able to apply the right tool for the given situation. Okay. Okay, so this is going to be on page, let's see, where are we here? All right, so we're going to start on page 21 of Unit 3. So page 21, page 21. And again, we're going to probably spend a couple of classes, a couple of lessons working on this particular idea. Okay, we want to get this really down pat before we move on too far. So let's see here what I said about it. Okay. Yeah. All right. So the sine law. Now you may actually see it written at the front title of the lesson said the law of sines. It's written both ways. Both are correct. We're going to call it the sine law. Just to be clear, it's the sine law. Okay, and it's the same sine, the sine ratio. That you saw in the previous unit, or sorry, the previous lesson, right? The trig identity for sine, it's the same sine that you use on your calculator. Okay, and we're just going to use it in a really cool way, actually. So now they have a definition here. I don't really like this definition. So I got my own definition. The sine law is an equation that equates the sines of the angles of a triangle to the lengths of its sides. Okay, that's it. Okay. So, they made their definition there is a little more complicated. Basically, you can use the sine law to find either angles or lengths of sides in any triangle as long as you have enough information. Okay. So here's the way the sine law is written. Okay. Take a look at this triangle. And remember at the beginning, way back at the beginning, probably, I don't know, a couple months ago, no, I guess it was last week, where we started talking about trigonometry, and I talked about the naming conventions of triangles. We name the angles capital letters, and then the opposite side then naturally gets the small version of that letter, right? So this is triangle ABC, right? I would write it triangle ABC like that. That's a triangle symbol. It may be a word in OG Cree, syllable anyway. I hope it's an okay syllable to use. Uh, Someone will have to tell me. Anyway, it's a little triangle symbol, and then it's ABC, right? Now, for the sides, then we can actually call this side here. We can call it side AB. Whoops, AB. Well, that really came out bad. I'm going to change colors here. We can call it side AB. Or, because it's opposite angle C, we can just call it side C. And that's what they've done here. They called it side C. Okay, so there's two different ways to refer to the side of a triangle. And it really just depends on the style that the particular writer is using. Okay, so just try and follow the style that you see in the text and in the examples as much as possible until you develop your own style. Okay, so the sine law then can be written in two different ways. The sine of angle A, so this is angle A, divided by the length of side A is equal to the sine of angle B, which is up at the top here. Angle B divided by the length of side B, which is equal to the sine of angle C over here divided by the length of side C. So what it is that the sine of this angle A, the ratio of the sine of angle A divided by the length of side A, the opposite side, is equal to, and so these ratios are all the same. Okay, and it's actually an interesting thing. If you have a protractor and a ruler, you can actually draw a triangle, work out those values, and you'll find that they all do come out to the same number, within a reasonable amount of rounding. But the other thing that we can do with this, remember that we can take the reciprocal of both sides of an equation. In the case where we have multiple equal signs, as long as we do the same thing to every single term between those equal signs, we're allowed to do that. So what we did was we flipped them over. We took the reciprocal over here in this other way of writing it. So again, as long as you're consistent, it doesn't matter which way you write it. You either put the angles on top or you put the sides on top. As long as you do it the same for all of them. Where students will go wrong is that they'll put the side on top in one, and then they'll put the angle on top in another, and that doesn't work. Okay, it's going to go horribly wrong, can't work, and it may seem like it's going to work, but no, it's not going to work. So now the next, this little bit here where it tells you how to recognize where you can use the sine law. I think if you do a few questions, you'll kind of quickly realize where it can come in handy. Okay, basically where you have, if you have an angle and a side and another angle, then you can find, that's going to be little z, you can find the unknown side there. Okay, so basically as long as you have two angles and a side, you can find the missing side, right? Or, and maybe they have a diagram on the next page. Yeah. Okay, so in the other case, you can have two sides and an angle, right? And then that can give you a missing angle. Okay. So those are two cases where you can use it. Now, there are some cases, some situations where you can't, even though you have a lot of information, you can't use the sine law. It's just not going to, you won't have enough of the right information. What I suggest you do when you're first getting started is that when you get a question, you think you might need the sine law, just pick one of these formats and just write in all the information you know, and just write sine A, sine B, or sine C, or whatever for the information you don't know. And what you're looking for is you have one whole one of these and at least one other piece of information. Then you can use it. Okay, but you definitely need one of these where you have the top and the bottom part. Okay. So then you can see that as long as we have at least one angle and one opposite side, then all we need is one other side or one other angle, and that's it to work it out. Okay, so we don't need all three of these terms. We only need two, and then we can apply our fabulous algebra skills, which you've been working on since the beginning of the course. You see how it's all working out? It's all kind of coming together here. So let's try one. Okay, well I'll put the answer up there. All right, what do we have here? So it says find the missing side as indicated. Oh, now it's telling us to use the law of sines. It's telling us which one to use. So let's work it out. Well, then we have our angle. So let's go sine. So the sine of 24 degrees. Now the measure that we put under there has to be the one that's opposite that, which is going to be 8. Let's call it meters. Okay, so 8 meters equals, okay, now we have the other one, which is sine of 39 degrees. So sine 39 degrees over, and it's the one that's opposite that angle, which is the x. That's our unknown. So there's our x. Okay, so now we have it. Now you're going to say to me, but Pete, the sine law has 3 equal signs in it. 2 equal signs, 3 terms. Why aren't we using the other one? And the reason is we don't need it. We only need one full one, right? We only need numerator and denominator complete, and then we need something in the other one, and then our unknown. And we can solve it. We have enough algebra skills right now to solve this problem. Okay? So having written it already, I realized that I made a terrible mistake. Not a mistake. I didn't know what we were looking for. I probably should have read the question a little better. We're actually looking for x. So the first thing I'm going to do is take the inverse of both sides, just to make things easier for me. So now I have 8 meters. Taking the inverse of both sides, if you had to explain that to someone that wasn't a math scholar like we are, we would say something like flipping them over, right? Flipping them over, flipping them upside down. Basically, we swap the numerators and denominators. Okay, you gotta be careful with that, but that's what we got. Okay, let me make those lines a little better. I kind of goofed a little bit there. Okay, so we flipped them over. We just put the numerators on top, the denominators. We put the denominators on top, the numerators on the bottom. We flipped them over just to get x up in the top, just to help us out here. So now we have to use our algebra skills to get x by itself. We can leave it on the right-hand side. That's not going to be a problem for us. Okay, so the way to do that then, and I'm going to change to blue, we're going to multiply both sides by the sine of 39 degrees. Now if we do that, then it's going to disappear on the right-hand side, and we're going to have it in the numerator on the left-hand side. Okay, so we're going to write it out. Now how you format this is entirely up to you, but just the convention is to put the number up front, and then put the, there you go. And then the bottom stays the same, sine 24 degrees equals, and then we're just left with x here, because by multiplying both sides by 39 degrees over here, it reduces to 1, and we end up with 1 times x, which is x. So now we have it, and the nice thing is that on the left-hand side here, we have everything we need to solve this problem. Okay. Now I see I just peeked over at the solution over here. I see that they put x on the left. Because this is an equal sign, there's absolutely no problem at this point in you reversing that, or you could have, in the last step where you took the inverse, you took the reciprocal of both sides, you could have also spun everything around the equal sign and put the x on the left and put everything else on the right. Okay, if that makes you, feel happier about it, and makes sense to you, then do it that way. Okay. There was certainly a time back in my early mathematics career when I did have to do it that way. It was hard to solve it this way. Okay, so I understand that. But in terms of mathematical notation, this is perfectly valid way of doing it. So now what we're going to do is we're going to take out our calculator, make sure that we're in degrees mode, and we're going to solve that equation right there. Okay, we got to make sure that you're in degrees mode, and this would be a good check here. So I'm just going to work out the sine of 39 degrees, and then I'm going to multiply it by 8. So I just did it a little backwards. Equals, and then divided by the sine of 24. Okay, and so indeed I got 12 point, and we'll just round to 1 decimal point equals x. Okay. Now notice I put units on here. It's really important. I know you don't put their units in the example, and it's because actually we don't have units. Sorry about that. Okay, sorry, this is one of those rare cases where we don't actually oh yeah, we have here. Sorry, we do. Okay, so they've given us a side. We can call it meters, so indeed I can let's see if I can do this. Did that work? Oh, look at that. No. Okay, really did work. Okay. So yes, so we have to put some units in there. Sometimes they don't give you enough information to figure out what the units are, and you just have to leave it as a number. But in this case, we had a side length, so we'll call it meters. It could have been kilometers, centimeters, because geometry is all about measuring stuff. All right, so that's how you do that. I'm probably just going to leave it right here because we definitely need to do some more on this, the law of sines, and we'll see all the other ways. So far, we've only used it to find a missing side. The other way we can use it is to find a missing angle, and then they may actually show us some cases where we don't have enough information to use it, but you know that there's another law coming, especially if you've peeked ahead in the unit. So there is another law that we can use to where the law of sines doesn't work for us. Okay, so let's just take a peek at this next question. All right, 2 minutes. So find the missing angle x using the law of sines. Okay, so in this case, it's the x. Now we're actually using it to find an angle rather than a side. Okay, so this question has units, the centimeters. So it's just a matter now of setting up and working out what we know and what we don't know. So we want to know the missing angle. So this time I'm going to be strategic about it. I'm going to say sine x. So now we have the unknown right in the numerator. Now it's divided by the opposite, 9.2 centimeters, equals, and now we're going to pick the other one that we know about. Sine 84 degrees divided by the opposite, 11.6 centimeters. And look at that. We have everything we need. Just a matter of getting sine x by itself. Okay. And then we're going to end up with a number for sine x. And then I bet you that the inverse sine function is going to come into play here as well. Indeed, it will. Okay, so I'll leave it there. Take a moment to work through that. Keep sending in those key questions. And thanks for joining us today. We'll pick this up tomorrow. Bye now. Right side on the road. Let's do this life.